Welcome, everybody. It's nice to welcome you from Krakow, which is now covered by snow. The weather is fine. I regret we could not meet here. We have a great guest who almost came from us from UK, but he came, David, only virtually. And David is known by few of us, especially by Camille, yes, who was his PhD student, and David was one of his advisors, and he used to work in London. Now he's close to Leeds. He's related to University of Leeds, and he will tell us today about coherent correlations in quantum channels. So please, David, thanks for visiting Krakow virtually.
Thank you. And I'll certainly be visiting it in reality, hopefully very soon. I think I've met a lot of really great representatives from the country, and the contribution to quantum information is certainly impressive. Okay, so just let me know if there are any problems or if you have any questions along the way, maybe via the chat or just unmute your microphone.
Now everything is fine.
Okay,
yes, we can hear you.
Great. Okay, so today I would like to talk about some work which I'm in the process of writing up, and hopefully will be put in an archive fairly soon. It is basically about estimating coherent correlations in quantum channels in efficient and robust ways. And this is work that is done in connection with two people, Christina, who's at Cambridge Quantum Computing, and Matt, who's a PhD student of mine. And I think he might be in this talk because I sent him the Zoom link. So if I say anything incorrect, Matt can pipe in and correct me. Okay, so let me just give a brief overview of what I'll talk about in the talk today, and then dive into it. So I'll begin by giving some background on the purpose and challenges of benchmarking quantum processes. I'll then introduce the idea of the unitarity of a channel and describe how it relates to benchmarking. And then I'll start to talk about some new ideas and new techniques, and introduce the idea of sub-unitarities and discuss some of their properties, and argue that they have many appealing features that you might be interested in. And perhaps most importantly, this question about estimating structural properties of channels in a way which is both efficient and robust. Okay, so that's basically going to be the content of what I'll talk about. Okay, so we're currently in the so-called NISQ-era, where we have noisy intermediate scale quantum devices, and we really want to get towards a full-scale, fault-tolerant quantum computer. But the reality is that we're still a fair way from that, and we have quite noisy devices. And so at the core of the development in quantum technologies is a question of control and certification, that we're actually doing what we're hoping to do. And so efficiently certifying quantum states and processes is a fundamental problem. And in particular, it turns out that correlative errors and coherence, these two aspects can bring their own challenges. Okay, well, the most obvious approach, you might say, would be to do channel tomography. I think someone's got their microphone still on, just FYI. Okay, good. So doing channel tomography is exponentially difficult, and so it's extremely difficult to do above a very small size. So it suffers from this problem of kind of cursor dimensionality, but it is also subject to what are called spam errors, which are errors that occur in the state preparation and measurement. So you might want to realize some sort of quantum circuit with particular unitaries, but noises inevitably occur. And so instead of a pure state and a unitary gate, and then a perfect idealized measurement, you'll generally have a mixed state, a noisy version of the unitary channel, and then some errors in the measurement. And so spam errors mean that it's hard to separate the errors that come from the preparation, from the gate itself, and also the measurement and the gates themselves. So firstly, I would say that it's we ultimately want to assess the actual channels that we realize in the lab and see how far they deviate from the idealized unitary gate. And so given an actual physical gate U tilde, we can always decompose it in terms of an effective noise channel composed with the target unitary. And so this you can always do because without any physical interpretation that this is actually how the noise occurs, simply because the effective noise channel can be defined as the actual physical channel composed with the inverse of the idealized unitary gate. Okay, good. Oh, and yeah, as I said before, if you have any questions, just chime in. Okay, so I said that quantum tomography is very hard to do, it's exponentially difficult, and it also suffers from spam errors. And so there are various techniques that have been developed to get around these obstacles. And an extremely powerful technique is called randomized benchmarking. And if you're interested in this, is an extremely nice recent review of the topic of certification in this link here. Okay, so let me just outline what randomized benchmarking involves, as it'll later on be form the basic skeleton of how we do our efficient estimation. So we might have a sequence of quantum gates, and as I mentioned before, there's an effective noise channel for each one. And for simplicity, we'll assume that the noise channel is identical no matter what gate you aim to do. This is an idealization, but it can be relaxed, and there's generalization to account for this. And so really, we're trying to do these idealized gates, but keep getting our noise, a certain amount of noise. And we want to assess how much noise is present. And so what we do is we look at this triple of gates, a perfect unitary composed with a noise gate and then a different unitary. And the trick is to reduce, use these degrees of freedom to simplify the noise channel and extract information about it from the actual physical device. And so what randomized benchmarking is based around is to ensure that the unitaries involved are sampled uniformly from the Clifford group. If you do this, so you randomly try and perform gates from the Clifford group uniformly, then you can show that the expectation value of this substructure here, this becomes a Haar average that acts on the quantum channel, the noise channel, and this generates a projection of the quantum channel. And so it projects the effective noise channel down to a depolarization channel.
David?
Yes?
Could you possibly do me a favor and remind the audience what is the Clifford group and to design, because maybe not everybody knows.
Right. So the Clifford group is I suppose the simplest way to view it is that if you consider Pauli unitaries on n qubits, so you could have a sequence of Pauli unitaries on n qubits, you want to know what unitaries, global unitaries, send Paulis into Paulis. And that is a group of unitaries, and that is simply the Clifford group. And so the Clifford group includes the Pauli unitaries themselves, but it includes non-Pauli gates as well. And there's a sense in which the Clifford group is computationally simple because circuits involving Clifford gates can be classically described efficiently. The two design aspect is really that if you average, well, the two design refers to wanting to replicate a Haar average. So if you imagine, let's take a qubit. So if you have a single qubit and a quantum state rho, you might wish to average over all possible unitaries you can do in that qubit. And so that you can have infinitely many rotations. And so the Haar average is the uniform average over all unitaries on that qubit. And this would collapse the qubit state down to the maximum mixed state. But in practice, you don't want to do infinitely many unitary gates. And so a T design or a two design is really about reducing down an infinite average over all possible unitaries to a finite number of unitary gates that perform the exact same averaging. And so for the qubit example, if instead of having a state rho and hitting it with infinitely like a random unitary, you hit it with apply one of the Pauli unitaries to it, identity X, Y, or Z, then and if you do that with equal probabilities, then it's exactly the same as if you had have averaged over the whole continuous infinity of unitary gates. And so this two design property is just that if you average over this discrete set of Clifford gates, then it behaves as if you've averaged over all unitaries. Okay, hopefully that's a little clearer.
Yes.
Sorry if yeah. Okay,
no,
great.
Thanks.
Okay, and so I described the Haar averaging for a qubit state, which collapses it to the maximum mixed state. But what is happening here is actually an average of a channel, because you're taking a channel here and you're distorting it to the left and to the right. And in the same way as the qubit state collapses to the maximum mixed state, you project onto the maximum mixed state. This net averaging averages the unknown channel E into the depolarization channel, which is just described by a single parameter. So a depolarization channel, when it acts on a state rho, it either leaves the state unchanged with some probability P, or replaces it with the maximum mixed state with probability 1 minus P. And so it's a single parameter family of quantum channels, which are extremely simple. And so the idea then is that by doing the circuit where you randomly sample from the discrete finite set of Clifford gates, you can reduce this block down to being effectively a very simple depolarization channel. And if you do this throughout the circuit, you're basically simplifying the effective noise channel down to always being a depolarization channel with some depolarization parameter P. But now the key aspect is that if you depolarize by a certain probability fraction P, K times, then it's exactly the same as if you have a depolarization by P to the power of K, just because the probabilities multiply. Because you get this P to the power of K here, by varying the number of these boxes, you can probe this. So the point is that this parameter P is a feature of the channel you want to estimate, and it's unknown to you. And you might not have control over this state here or how good the measurement is here, but you can control K, the number of times that this effective depolarization channel acts on the state here. And if you do the calculation of the probability, if this is say a binary outcome, like a projector, then a simple calculation on this quantum state passed through this partial depolarization channel sequence is that the probability obeys a power law in P. And the errors due to state preparation and measurement are all bundled into constants A and B. But the property that you would like to know and assess, in other words, how noisy is the effective noise channel, P, is exactly captured by the statistics of these empirical data. And so if you vary K, you can fit like a power law decay and determine what P is. And you can do this without ever having to worry about the state preparation and measurement errors. And so from this randomized benchmarking protocol, we extract a number P, which is the effective depolarization of the hidden noise channel E. And it turns out that this parameter P is directly related to this average here, which is called the average gate fidelity. And this average gate fidelity is just an average over all pure quantum states, and it measures how much this effective noise channel differs from the identity channel. And 1 minus this average fidelity is called the infidelity or average gate error. Okay, so that's the core of randomized benchmarking. It's really about saying we have some unknown and complicated channel E. Let's project it down to something simpler, and that simpler thing gives us a decay law. And for that decay law, we can read off a parameter. So that's a key idea. And this can be done efficiently and in a way which is not sensitive to spam errors. Okay. So to motivate what I'm going to talk about, let me highlight some limitations with this. With quantum computers, and in particular the fault-tolerant theorem, there's this measure for quantum channels called the diamond norm, and this is a very awkward thing to calculate empirically. If we could do it, we would have done it already. So it's a particular type of norm which measures like a distance, and it's a distance of the noise that is present from the identity channel. And so this is difficult, but we've shown that this infidelity or average gate error can be estimated efficiently. However, the idealized quantity we want to know is upper and lower bounded by this average gate error in a way which which does matter. It's lower bounded by r to the 1 and upper bounded by the square root of r. And so if your favorite quantum computer engineer puts on the website that, oh, we have an average gate fidelity for our quantum device of 10 to the minus 4, well, because of this square root versus linear power, this means that the diamond norm distance could vary by 2 orders of magnitude. And so this information is not necessarily very informative, because the thing you want to know could differ by 2 orders of magnitude. And while the scaling with this parameter r is linear for simple types of errors such as dephasing, for unitary errors, it scales with the upper bound, this square root power, which says that, well, if this was a unitary error, then r being 10 to the minus 4 might give the impression you're doing very, very well, when in reality the error is more like 1%. And so the limitations is a weak link with the diamond norm, and coherence is a challenge. And so this then motivated the introduction of coherence measures, and the one that is relevant to us here today is called the unitarity of a quantum channel. And what this is, it's a slightly counterintuitive average over all pure states, but it in some sense measures the square purity of the output. And so if this average is 1, then E is unitary, so it's a signature of a unitary error. And if this is 0, it's a completely depolarization channel. And so it quantifies this parameter, this regime between depolarization and unitary errors. Yes?
One more remark.
Yes,
so
sure.
You mentioned there's another quantity like average purity of the output. And the difference is, the main progress here in this definition is that it works also for not bistochastic, so not unital channel. Because if you have a maximally contractive channel which sends everything to the pure state, of course, there is a huge contraction, but the average output is pure. So this measure is able to distinguish both cases, yes?
Yes, exactly.
So it's particularly useful for non-unital channels, this measure.
Exactly. And this is really what this factor of identity over D captures here.
Yeah.
So you're not simply measuring the purity of the output state, but
with respect to the image of center, yes, of the ball.
Exactly. And in fact, well, actually, the next slide actually relates to work by people in the group. Let's see. Oh, no, sorry, the following one. Okay. But this particular quantity, as I said, its virtue is it witnesses this bad scaling, this r to the half versus linear r. And okay, you don't need to pay attention to this. There's basically a general relationship between the unitarity U and the average gate error R. And there's a theorem that tells you exactly when you have a nice scaling between the diamond norm and the average gate error. And this occurs under this condition. And so, but the take-home message here is that U is an independent, the unitarity is an independent parameter which from the average gate error, which can also be estimated efficiently with benchmarking techniques, and it gives information as to the coherence of the effective noise channel in your device. Okay, great. Now, there's a very interesting perspective on the unitarity.
I have a question. I mean, this expression, it is right expression, the theorem already looks like it has O of R2 scaling. I mean, there is 1 minus R times constant squared. Yes, yes.
Ah, yes, but this is an this is an inequality, not an equality.
Okay.
And so for example, for a unitary, for if E is a unitary, or say confined to unitaries, then this is exactly equal to 1. And so you don't have this scaling here.
Okay.
And so the point is that U and R are generally independent. They obey a bound, but U gives independent information. And so if you estimate U and R, and this condition does not hold.
Okay, yeah, so the difference grows as R squared.
Exactly.
Okay, yeah. Okay.
Okay. Excellent. So there's a really nice perspective on the unitarity of a quantum channel, which is actually due to, I guess, everyone here, everyone in this paper is in the group. I'm not sure. But it's actually a very small comment that was made in the paper as an aside. And as Carol said, that this quantity is good for non-neutral channels, and it's a funny average. But if you view the channel acting on a pure state as a random variable outputting an operator, then you can re-express the unitarity essentially as a variance measure, describing the variance or noisiness of the channel. And so I really like this perspective because it allows you to compare with classical random variables, where the variance of a random variable describes how noisy the random variable is. And so we have the unitarity being analogous to this variance. But then you can ask, well, you have a notion of covariance, and covariance measures correlations between two random variables. Is there a comparable type of measure for quantum channels that is either related to the unitarity or is based around the unitarity in a way that can be efficiently measured like the unitarity? And so this is the target for the remainder of the talk. So it's really, so maybe it's important to emphasize that while in classical theory, it's always possible to describe a whole range of entropy functions and single-shot entropy functions, which are very sophisticated and complex. Ultimately, we look at variance and covariance because they're practically useful and can be estimated very simply. And so we have an analogous type of scenario here. And so we can therefore ask more generally, are there unitarity-based quantities which give us additional insights into quantum channels in a way that can be efficiently estimated in a robust, spam-robust way? And so, okay, so we can now ask, is there a unitarity-based measure of correlations in a quantum channel? Meaning we would like to tell whether our noise channel or is either uncorrelated and you have a product channel action, or is not a product channel but has some sort of correlative errors. And so what we have developed is what is called correlated unitarity. And so let me first put down the core structure of it and then explain the individual terms. Firstly, the most important thing to do is compare with the covariance measure. The covariance between two random variables is the average of the product minus the product of their averages. And so this correlated unitarity is mimicking that. We have a joint unitarity, which is describing the coherence that is present in, so you've got two quantum systems, A and B, and it's quantifying the amount of coherence in as the unitarity quantifies it of the composite system. But then you want to subtract away the coherence preservation that occurs only from A to A and only from B to B. And so the difference between these two terms is to determine what are the correlative errors, the correlative structures of the channel. So how do we, so these circles or ellipses you should understand these to be measures, unitarity measures for coherence flowing in parts or subsystems of the total system. So how do we define these? Well, let's take the most simple one. And so we can refer to this as a sub-unitarity because it's referring to the measure of coherence that is preserved in one of the subsystems. So A, for example. So we'd like to know how much coherence a given quantum channel preserves going from A to A. Well, we have our bipartite quantum channel. And the most natural way to define it is if we could, so we want to know how much, viewed like water almost, you want to know how much coherence flows from the input A to the output A. Well, if we turn off all coherence for B by putting in the maximum mixed state, and then only look on the output on A, then we can define the sub-unitarity A to A, measuring the coherences from A to A, as simply the unitarity of this resultant channel, EA. And so this is a very simple definition, and it turns out to work well in practice.
Sorry, David, so this EA is simply this resulting channel EA is like the trace of the second subsystem if you introduce the maximal mixed, right?
Yes, yes. So
okay.
There's a challenge that if you have a bipartite quantum channel, in general, you don't have a uniquely defined marginal channel. Because it depends on what state you put in here. But if you want to quantify coherences specifically, then it makes sense to switch off all coherences on B. And this allows you to measure exactly how much coherence is preserved between A to A. Okay, good.
Yes, a short remark, if I may.
Sure.
If for EAB, we set a unitary bipartite unitary gate, then
Yes.
this channel EA is sometimes called unistochastic channel, in a sense that it is determined by the unitary gate of the increased size and square.
Yes, I see. Ah, yes.
Yeah. So this is somehow a relation to this setup.
Yes, 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 exactly. Yeah, I haven't thought of these sub-unitarities in terms of unistochasticity. I suppose I suppose one challenge is that this is just one component required to measure the correlated unitarity. But in some sense, this is the most physically natural way to define it. But as you'll see, there's a whole range of possible sub-unitarities that one can address.
Okay, I see.
So for as an example, you could also consider the sub-unitarity from A to B, meaning a unitarity measure of the coherence that goes from A to the output system on B. So in other words, how much coherence is flowing to the environment, if you like, if A is your primary system.
So this is sometimes called a complementary channel or something like
Exactly.
this.
Yes, exactly. And so, well, you can define it essentially. I mean, this is simple again to define. You just swap your two output systems and then measure the unitarity of this output system. So in other words, these should be swapped. Yeah. There should be a swap. Oh wait, is that true? No. This is right.
No, I think
because,
it's fine.
Yeah, coherence comes in here, and the idea is it flows down here and then out there. And so this is obviously related to the A to A subunitarity just by doing a swap. Excellent. But then if you think about it, there's a whole family of subunitarities. You can have essentially, if you pick any input subsystem, you can consider the coherences from that input subsystem to some output subsystem. And you can have a corresponding subunitarity describing the coherences flowing. So in this case here, you can describe, this AB to A subunitarity is measuring the coherences that are purely relational. So they're not local to A or B, but are relational coherences between A and B. And so this subunitarity will measure the coherences that are localized to A. Okay, so we need some sort of organizational principle to handle all these subunitarities. And we also need concrete mathematics. And so we do this by the Liouville representation of a quantum channel. And so the Liouville representation of a quantum channel can be viewed essentially as the matrix components of a quantum channel. And it's the matrix in a particular basis. So we imagine the quantum channel acting on a basis matrix, and then we take the trace with of the output with some other basis matrix. And the basis of matrices we choose is, well, the x0 will be proportional to the identity, so we'll have non-zero trace. And then the other ones are traceless. And so you can just imagine this as all possible combinations of Pauli matrices, which have zero trace. And so the Liouville representation is this d squared by d squared matrix of numbers, which gives a complete specification of the channel, because it gives a complete specification because these are a complete basis for all matrices. And so if you separate out the trace part from the traceless part, yeah. Is there a question?
No, please continue. I will have a comment later on. Sorry.
Okay, sure. Then the Liouville matrix for a channel can be written in this form here, where the one comes, this top row here comes from the fact that the channel is trace preserving and completely positive. But the thing I want to focus in on is this Tij component. And this X here is describing the non-unitality of the channel. This X is essentially the block vector if you act the channel on the maximum mixed state, the resultant state has a generalized block vector X. And so yeah.
A short comment perhaps. So
sure.
This could be also viewed as a so-called Fano form of the Choi-Janowski state, which represents the operation of the channel epsilon, and then just X is the marginal, and T is distortion matrix or correlation matrix between two subsystems. Yes. So it's just
Yes.
a way of looking at this formula.
Yes, indeed.
Or sometimes it's called also the Bloch representation of a channel.
Yes. Yes. Yeah. The Choi representation is generally a much nicer representation, but in this case, for what we do, it turns out that the Liouville representation is the most compact one. Yeah, it's kind of a quirky thing. But the key thing here is that the unitarity of the channel is actually given by this simple quantity here, which is purely in terms of the traceless, the matrix Tij for the traceless components. And it is trace T dagger T. And if you know the Hilbert-Schmidt norm, then this is basically the square Hilbert-Schmidt norm of this matrix times a constant. And so this is very, very simple quantity. Now, but we're interested in bipartite quantum channels. And so if we consider a bipartite channel structure, then we have a bases at A and B. So x0, x and y, x refers to A and y refers to B bases. And you can expand the Liouville representation of the bipartite channel in this rather complicated matrix. But the point I want to emphasize is here that the traceless part divides up into three separate submatrices, with A to A referring to traceless part of A being sent to the traceless part of A. And so this notation is exactly the same as this sub-unitarity description. And so our sub-unitarities are actually defined in terms of the measure of these subblocks for this Liouville representation. And so for a given input subsystem X and an output subsystem Y, we define the sub-unitarity associated to that as, by analogy with the unitarity, as a trace T dagger T for the corresponding T matrix block. And there's a normalization constant, which I won't worry about. And so this is a natural generalization of the unitarity. Okay, excellent. But it also coincides with the particular definitions of the sub-unitarities that I gave earlier, but it generalizes them. It also has some extremely nice, so let's see, I suppose I've got maybe 10 to 15 minutes. So yeah, okay, good. I think I'm almost on schedule.
Yes, it's fine.
Okay, so sure, okay, I've given this definition, but what is this? We can ask firstly, well, we've got two questions. Do these sub-unitarities have nice properties, firstly? Secondly, can we efficiently estimate them in some spam robust way? So firstly, let me outline some properties of them, which I might have to go a little quicker through than I aim for, but let's see. Well, the first nice property of these sub-unitarities is that the total unitarity of the bipartite channel is actually just a weighted sum over sub-unitarities. And so this is a natural and appealing aspect, that yes, we can estimate this with randomized benchmarking, but formally it decomposes into a weighted sum of these coherent contributions. And so this is a nice appealing result. The proof of this actually is essentially Pythagoras' theorem. It's because these different blocks are independent, they're orthogonal blocks. And if you just expand the total unitarity definition, you just get this sum. Okay, that's not one nice property. But a more interesting one is that it's possible to show that unitarity as a measure is monogamous. So what do I mean by that? Again, through a very simple calculation, essentially Pythagoras' theorem and a particular bound, you can show that the sub-unitarities, the sum of the sub-unitarities A to A prime, where A prime is the output system, and A to B prime, that sum is always less than or equal to 1. So you should view this as like an incompressible fluid, and you've got a unit amount, and it flows, and a certain amount flows out from A, and a certain amount flows out from B. But the sum will always be less than or equal to 1. Well, these subunitarities don't have, I mean, we've introduced them, and okay, this obeys a particular inequality, but we prefer to relate this to concretely the unitarity itself. Well, if we consider a channel with a single input and 2 outputs, then these subunitarities actually coincide with the unitarities of the marginal channel on A and the marginal channel on B.
I'm sorry, David. So
Yes.
Here in this picture, the input is of what size, or what are the sizes of the output A and B?
It's completely arbitrary now. So any dimension.
Okay.
So this completely general quantum channel, arbitrary dimension for some input system, arbitrary dimension A and B output. Yeah.
Okay, so the dimensions, you assume they do not need to be equal on left side and right side?
No.
Okay.
So it's a slight extension. Yeah.
Okay.
But the nice thing is we now discover the unitarity as a measure of coherence is monogamous, meaning that you cannot simultaneously have high unitarity on the output port and A and the output port B. This is a kind of a compact description of the information-disturbance theorem. Okay, well, if this is close to being unitary, this has to be very far from being unitary. Let me not say anything more about this right now. So I've talked about the subunitarities leading to monogamy relations, but we said earlier that we really wanted to get a handle on correlated coherences. And I said I introduced this measure which generalized the kind of covariance between 2 random variables. And this measures the correlations that occur in the bipartite channel. And this is built up of these 3 subunitarities. And it turns out that this also has very nice properties. This measure of correlations is invariant in their local unitaries. In fact, it also has monotonicity properties. It's bounded between 0 and 1. It vanishes on product channels, which is what we'd want it to. And it's maximized on the swap channel. So where you completely swap your 2 quantum systems. But perhaps more interestingly, it provides a witness of non-separability of a quantum channel. So what do I mean by this? You can define a separable quantum channel as being a convex sum, a probabilistic mixture of a products channels. And it turns out that if you calculate how large the correlated unitarity can be over all these type of channels, there's an upper bound which is strictly away from 1. The proof actually is extremely non-trivial, which is surprising, but it's been torturing us for a month or so. But we're basically done with it. But the point is that
nothing.
I said or so. I don't want to admit how long we've been tortured by it. But the point is that if you measure the correlated unitarity and it's above this value, then you know for certain the channel is not separable. Okay, so there's some nice structural properties, but in the last 5 minutes, I'll try and talk about how these can be efficiently estimated. Okay, so the question is, can we, okay, nice properties, gets at some really interesting structural aspects, but can they be done in the lab in an efficient way? Okay, so let me explain that how this can be done and also what obstacles exist. So I mentioned before for randomized benchmarking that we relied on these Clifford averaging maneuvers, where we sample from a finite set of unitaries that allow us to mimic a uniform averaging procedure. And the uniform averaging procedure coarse grains the channel to some simpler channel. Well, what we can do is replicate this procedure, but now doing a local twirls, meaning we don't choose Clifford unitaries over the composite system, but only do it locally. So on A and B separately. So you can imagine Pauli X, Pauli Y, Pauli Y, Pauli Z. Yeah. So only product unitaries and product Cliffords. Okay, technically this also does a kind of projection or coarse graining of this channel. And we'd like to know, can we use this to extract meaningful information about the correlations, the coherent correlations in this channel? Well, this is an actual circuit of the protocol for addressing or estimating sub-unitarities. So what we have is we've got some noisy state that we can't quite control, but then we have this sequence of idealized unitaries and effective noise channels. And so we choose an I1, J1 for the first round. These are Clifford unitaries, and then I2, J2 for the second round, and so on and so on. And we do this K times. And so we have some sequence of Clifford gates that we randomly sample. So we just do this over and over and over. And then we now measure the expectation value of some observable, which again can be subject to measurement errors. And what we do is we get, so the sigma S is whatever resultant state comes out of here, and it depends on the sequence of Clifford unitaries, S. And we square the expectation value. Now, if we do this many, many times and average over different unitary sequences, then it can be shown that this quantity, which can be efficiently calculated, obeys a power law with the decay parameters being three of them, three different ones. So you've got constants given by C, 0, 0, and 0, 1, and so on. These, again, contain the spam errors due to the state and measurement errors. But there's a kernel of robust information that we're extracting out. The eigenvalues, parameters lambda 1, lambda 2, lambda 3. And if you go through the analysis, it can be shown that these eigenvalues, these lambdas are actually eigenvalues of a 3x3 matrix. And the 3x3 matrix is exactly the 3x3 matrix of sub-unitarities. And therefore, we can efficiently extract data about the sub-unitarities, but it's slightly harder to get at because these are the eigenvalues of this matrix and not the individual entries. But there are tricks we can still play that allow us to estimate the things we actually want to estimate. So let me briefly mention two or three simplifications. So this matrix of sub-unitarities, If you restrict to product states, then this matrix of sub-unitarity simplifies a great deal. So for product channels, the eigenvalues are really of a very simple form. They're some number describing the unitarity of A, some number describing the unitarity of B, and the product of them. And because of the form of these eigenvalues when restricted to product channels, it turns out that if you do your benchmarking protocol and estimate the numbers lambda 1, lambda 2, lambda 3, then this quantity here, the non-zero-ness of this, is in some sense a measure of correlations. But this is a bit ad hoc and messy. This scatter plot just shows that typically it works pretty well. And is close to the correlated unitarity, but it's a bit of a ugly fix. What one would really want to do is estimate the sub-unitarities in this definition, and not and so have a handle on the A to A sub-unitarity or the B to B. Well, I said that local twirling gives you the eigenvalues of this matrix. Now, if you, but that also means we've got access to the trace of this matrix. So, because the trace of the eigenvalues equals the trace of the matrix. And so the sum of the eigenvalues which you can estimate are the sum of these three sub-unitarities. So if we could estimate the sub-unitarity A to A and B to B separately, then we could estimate the full quantity UC. This, however, runs into a problem because in order to do this, we would have to have control over definitely inputting the maximum mixed state. Because for this sub-unitarity, you need to switch off all coherences. It turns out, so it's not spam robust because you have to prepare a particular state, but because the state is particularly easy, it's not so bad. Okay, so it actually turns out it works out pretty well in practice, and it's efficient. Okay, I don't have time to talk about this, but if you restrict to Pauli channels, it turns out you can do everything purely robustly, spam robust and efficient, but we still have a fully spam robust protocol. Okay, I'm running over time a little bit, so let me quickly just sum up the state of the art. Okay, we've got nice, interesting measures that get at the substructures of quantum channels and can be used to tackle interesting structural problems. But the important thing that is vital to emphasize is that we want something which is efficiently estimatable in a spam robust way. The open questions remaining are, there are many of them. For example, we should apply this type of theoretical framework to actual devices. What coherent information does it give us about, say, crosstalk errors in actual quantum computers? We would like a more satisfying spam robust method, but maybe more interestingly would be to combine our existing methods with other methods in the literature, such as spectral tomography or shadow tomography. And also the idea of addressing what structures of quantum information can be efficiently estimated and probed with state-of-art experiments. Okay, we're writing this up and it'll be on archive soon, but I'll leave it there. And if you have any questions, then I'd be happy to address them. Thank you.
Thank you very much. Yes. Very nice talk. And then it's very nice for us to listen to a native English speaker. Always a nice experience. So let us start the discussion. Who would like to pose the first question? Mine is 0, so I hope you will let us know when we have to look into archive, or you will send us your preprint, which looks very interesting to us. Yes.
Thank you.
I can start maybe with a maybe not simple, but like a question that is not directly related to this. But have you considered doing this experimentally, like using those IBM quantum experience and stuff? Because I know that randomized benchmarking are the experiments that people do the most there.
Mm-hmm. Yes, I have a PhD student who is actually in the meeting here, who is going to be doing this, and we're going to be doing this with Christina, who's at Cambridge Quantum Computing and has top secret access to all sorts of quantum computers, apparently.
Yes, so we see Matt at the audience. Hello, Matt. Thanks for coming here. Matt James, yes.
Yeah. Hi.
Hi.
Yeah.
And then the other question was, so you were looking at the correlated unitarity, or is there any other measure out there for correlations and purity of channels, like correlated purity or correlated infidelity? Or I haven't thought about this ever, so I'm just asking.
I looked at this a little bit, and I really didn't see much. Because you kind of think surely someone's done this. I do know that maybe about 6 months ago, Gila Gore brought out a paper on essentially resource theoretic formulations of entanglement in quantum channels. So kind of like dynamical entanglement. And so this is probably the only work that at least I know that addresses the correlative structure of quantum channels. The downside of that is resource theoretic measures are quite far from actual experiment, and and it's very easy to find some sort of abstract single shot entropy. We've all done it, but it's harder to define a measure which might have flaws and weaknesses in an abstract way, but in practical terms still gets at what you want to get at.
Yeah. Okay. Thank you.
Fine.
I have perhaps
Konrad, yes?
Yes, I have perhaps uneducated question. Let's call it this way. Is the channel separable if its Choi matrix is separable?
No.
It's not exactly that, because it's separable if and only if it's the Choi state is separable across a particular bipartite splitting.
Yes, because there are many possible cuts, but yeah.
Yeah, actually, you can see this just by looking at well, the identity channel. Yeah, well, the identity channel would be maximally mixed. Sorry, maximally entangled. So yeah, it doesn't map across to the Choi state in a nice way.
I see.
Yeah.
If I may add something, Konrad, look, to have separable channels, you have channels which act on bipartite system.
Yes.
And if you take a simple system, channel acting on simple system, the Choi matrix is already in the extended space.
Yes,
so
it's
you can
like
act,
4 times larger.
Yeah, exactly. So you can, the first question one can pose, separability of Choi matrix can consider also channels acting on simple monopartite systems for which no separability is possible. So it's a simple answer that they are not quite related. By the way, David, could you please go back and show me this picture, just 2 pictures above with the egg? I like no, up.
Yes.
Yes, here. Yes, exactly. So this was in a sense related to the question of Konrad. So is it fair to say that this definition is somehow analogous to the standard definition of separable states? And this picture here, sep corresponds to separable states. And this would be like more or less analogous to Werner states, which join the center of the body of states to the maximally entangled states, and at some place they go out of the set of separable states?
Right, I see. Yeah, firstly, I'd say it's definitely analogous to the separable state scenario. And in fact, if these local channels EK and FK are state preparation channels, then it's exactly the definition of separable states. In terms of the Werner states, it's not obvious how that maps across.
Well, it's only an analogy that this line you could somehow relate to the famous, well-known line of Werner.
Yes, exactly. It's exactly that.
I don't claim it's the same. I only say that if you, let's say, study the things, you can basically see kind of an analogy.
Yes, this quantity is a witness of non-separability.
Yes, something like this. Yes,
definitely. Yes. Yeah. In other words, if you get any value above this, actually, we still don't know what this optimal value is. We have a very poor upper bound, which goes as 1/d to the 4th. But we're almost certain that this is much lower, or lower anyway. Yes. But so the swap unitary maximizes this correlation, because you're then really transporting all the coherence of A to B and all of the coherences from B to A. But yeah, we don't know anything beyond this. Actually, it's all unclear. So I think I would say that it's also open to debate whether this is the ideal measure of correlations or not. It's because we really went by analogy with the covariance of two random variables. Yeah, but I think there's theoretical work to be done to assess whether this is actually the best type of measure one could use.
Thank you very much. Are there any other questions?
Yeah, I have a couple. So firstly, so your experiment, your diagram has these rounds, right? So you do some Cliffords, you do your epsilon, you do some Cliffords, you do your epsilon, and so on. So is it possible to estimate how many rounds of this structure you need? Like, do I have to do hundreds of Cliffords or billions, or like where?
Right. Yes. There is. So we haven't done it for this correlated or sub-unitarity setting, but it has been done for standard unitarity benchmarking. I believe Stephanie Venner's group. And it's, I suppose it depends what you mean by efficient. You can have efficient in being polynomial, but or efficient in reality. Yeah, because even, for example, uniformly sampling Clifford gates it poses problems. And so I think the simple answer would be it is formally efficient, but practically, I think a lot more needs to be done to assess this. So I don't know.
I have a second question, which is maybe a bit mean, but
that's okay. I asked you. I asked you tons of questions in your PhD.
Yeah, you did. So I guess the obvious reason to focus on like 2 input, 2 output channels is that you can say useful things in this setting. But is there any hope of saying something about like increasing the number of horizontal lines on this diagram, basically? Like, can you say anything about channels?
Horizontal or vertical?
Horizontal, right? So can I add more systems, basically?
Oh yeah, more systems. Sure. I mean, that's certainly the case. I think the problem with that is that the state of the art in terms of understanding these sub-unitarities is very much in its infancy, and we've really been kind of seeing what works in practice, and so I would say we do not have a clean handle on this type of sub-unitarity approach in the way that, say, classical random variable theory, you just like you'd have like, oh, moment structure, you know, cumulants, blah blah blah, inequalities. Yeah, so I think even before going to multi-partite scenarios, I think it would probably be better to abstract away the definitions in a way which is independent of the Liouville representation. I think the Liouville representation was just convenient and it clearly works, has some nice properties, but we try to look at defining things in the Choi picture, but actually it gets very complicated. And I almost feel like it might be worthwhile stepping back and saying, okay, what structures do we want to generalize from, say, classical theory into quantum theory, whether it be at the level of states or channels, but with the idea being some sort of low order moment estimation. And so I think this is a very interesting direction. And already the bipartite scenario, it's not clear. Good
Thank
question.
you. That sounds good.
Okay. Thank you. Thank you very much for the question and answers. And let us thank the speaker again for the visit in Krakow.